So those of you at home that are running BTRFS, have you set up a cron job with BTRFS Scrub start? And are you emailing yourself the results of that cron job? Because you probably should be if you're not. Alright, so we've got our RAID controller installed. This is a hardware RAID controller. This is a PERK 5. This is all I had laying around. This is pretty similar to LSI or HP Mega RAID or any of those. This is a hardware RAID controller. It has error correcting RAM. It has a battery backup unit, which will allow for write-back caching, which should prevent the RAID write hole where you've got a block of data and it's being in the process of being written to all the disks in the array, but then power's lost or something weird happens, something crashes. It's like, did everything get written to all the disks? You don't know, so that's the RAID write hole. So we boot it up, and we hit Control R to go into the RAID, because that's the thing. So we're going to do this. We're going to do RAID 5. It sees all three of our disks. Good. It's going to be 1.4 terabytes. Good. We're just going to call it VD1 because it doesn't matter. We're not going to give it read ahead. Write back is fine. Yeah, this is all fine. I'm just going to tell it OK. Now we're going to initialize this, I think. We're going to do fast int because we're lazy. And it's online. RAID 5, optimal, 1.363 terabytes. Close enough. Now we should be able to boot into Linux and format the drive and mount it and then completely fill it with crap, just like we did with the MD array. What we're going to do, look for our drive, SDA. All right, fdisk, dev SDA. We've created a partition, nkfs.ext4, dev SDA1. This is going to create a file system on our new partition, our new 1.4 terabyte partition, and then mount sandbox. We've got our dummy file maker dot. Let's just take a look at it real quick. 500 meg works for me. So we're going to run the dummy file maker and then run IOTop just as kind of a sanity check and make sure that that's running at a reasonable speed. Nope. Oh, this is the old version. So devu random is too slow. We're going to use dev0 instead, and then we're going to overwrite with random ones. But it means every file is going to have the same MD5 sum, but that means it'll be easier to spot. So, all right, so we can see from IOTop that it's writing around 100, 150, peaking at 200 megabytes per second. It's going to take a while to fill 1.4 terabytes. Several hours at least. And it's going to slow down as it gets farther into the disks. So we will just wait for it to complete. Okay, so we've got our PERK set up. This is our hardware RAID controller. This is basically the same setup as we saw on the other machine. We just created a whole bunch of empty files. The results file contains the MD5 sum. It's the same in all of them because it's just full of zeros. We're going to shut down and inject a bunch of ones randomly on one of the drives. And now you may be thinking, well, wait a minute, what about patrol read? Maybe if we let it do a patrol read, or maybe if we let it do some kind of a process that it would correct it, because it's a hardware RAID controller and it should totally do that. So no, you misunderstand how RAID patrol read works on these hardware RAID controllers. Here's the thought experiment to confirm that you understand how it works. So you've got the hardware RAID controller. You set up a RAID 1 array, so we're talking about a RAID 5, but thought experiment. You got RAID 1, you got two identical drives. You set up, you do all your stuff. You pull one of the drives from the controller, you direct attach it. You can mount it. It shows up as normal, file system. You can mount it. You can do all the stuff that you would normally do with the file system. So it's basically an ordinary hard drive. You don't need the controller to be able to read the data from the hard drive in the case of RAID 1 because it's ordinary information just mirrored across both disks. So if that's the case, and it's RAID 1, and both drives are identical, and you've pulled one drive, separated it from the controller, and you're using it, suppose that the scenario that we're talking about happens, which is you have bad data, and the data is not reported as bad by the controller or by the drive. A read error is not detected by the controller, I should say, as reported by the drive. How does the controller know which drive to believe? If it's RAID 1, there's no extra information on the drive. You have demonstrated by taking that drive and plugging it in without the controller that the controller doesn't do anything special to the data that's being written to the drive. And it probably shouldn't. Because it's not doing anything special with the data, how does it know which data is correct and which data isn't? Well, it doesn't, and that's the answer, and that's why you got to understand that patrol reads don't really help you. And so we can actually look at the definition for patrol read in this particular case for the PERK RAID 5, which is it's designed as a preventative measure that includes a review of your system for possible physical disk errors that could lead to physical disk failure and damage data integrity. So patrol read is predicated on the fact that when the controller goes to read a sector, that the drive returns, oh, I can't read the sector, I don't know what's in it, as opposed to just returning the wrong data. And so, you know, is that a pretty common way that drives fail? Yeah, absolutely. Drives will report that they can't read a sector all the time. But drives will also report, more often than we'd like to admit, that, you know, oh yeah, I was totally able to read that. And no, it totally wasn't. Drives can also manage their bad sectors internally. So like internally, the drive can say, oh, you know, I did have a read error, but I was able to read it and I corrected it. And you can get at some of those variables through smart. So like when you're doing smart queries and things like that, you can get at some of that information. And some controllers are designed to read from and understand that information. And so if the error count, like the grown error count as reported by smart, is growing too quickly, some controllers will flag that and say, oh, this drive is dying. But for our purposes, we're just going to take one of the drives, we're going to corrupt the information a little bit, we're going to put it back in. Now, if we just left the drive out, the RAID 5 array would recover. It'll have all the information. But as you'll see, when we put the drive back in with corrupt information, the controller is not going to know which drive to pull information from, and we're going to have corrupt information. Even though we do actually have correct information in the parity, the controller has no way of knowing which data is correct and which data isn't. And thus you have bit rot. Okay, so we've booted back up, and after having switched the disk, and I'm just going to do fdisk-L grep 698 because I know it's 698 gigabytes. So we see let's dev SDA. So this is not through the controller anymore, it's directly attached to the motherboard. And if we do, well, we just do less because it's not a regular file. You know, we can see that there's all kinds of stuff there. And so what we're going to do is run the script that randomly, it's only going to put 1,000 4 kilobyte blocks. So we're talking about 4 megabytes of badness in 698 gigabytes. Now it's completely full of information, so we are going to see what happens and see if the controller can deal with that situation. Okay, now we've got our script set up, so we're just going to run it. Random DD is going to read from the random sectors.txt file and overwrite the random sectors with 4 512 byte blocks or 1 4 kilobyte block, because you may be, if you're doing this test at home, you may be using a more modern disk, in which case you're going to have 4 kilobyte sectors. And so this way, for this test, we just did everything with 4 kilobyte sectors, just because. Well, there it goes. It's going to do 1,000 random 4 kilobyte overwrites. So it's going to take a little bit. Not really very long. But you know, honestly, I don't know if you can hear it in the mic, but the hard drive made quite a bit of noise. And just to verify, I'm going to comment out the line. So it was 1,000 lines of output. So we've written 4 megabytes, just 4 megabytes of information. That's it, to 750 gigabytes by power of 10. And we're going to put that back in the RAID controller. Now we're going to try to read our files and see what's up. So we're going to just go ahead and halt this machine. And it's going to go down for a halt now. Okay, we're rebooting for the first time after doing terrible things to only one of 3 disks in the array. And so what we're on now is we're waiting for the Power Edge Expandable RAID Controller, PERC 5, to initialize its firmware and detect the disk. And if we didn't screw up the disk too badly, because remember, we only wrote 1 megabyte to it. Oh, look, no errors reported at all. 1 drive handled by BIOS, 1 drive, you know, on the adapter. It doesn't say anything about a degraded disk or errors detected or anything like that. We wouldn't really expect it to, because, you know, in the BIOS screen, it's not really reasonable for it to scan all 700 gigabytes. And, you know, odds are that we would have written something that the controller would notice that was sort of off kilter is pretty low, because it, you know, it can't scan all 700 gigs or, you know, terabytes, depending on what kind of disk you've got. So it really just initializes, and it's like, yeah, everything seems like everything's fine. So we'll boot up. So we'll wait for the machine to boot up, and then we'll mount that partition, and then we'll start a series of MD5 sums on the files that are on that partition to see if the MD5 sums have changed. And I think we're going to find that they have. And the controller, even though the controller, you know, we're talking RAID 5, and so if it was just 2 out of the 3 drives, it can recover from that situation. But in this situation, we have 3 out of 3 drives, one drive reporting erroneous data, but otherwise not reporting any errors, and it's not going to be able to recover from that. The controller is not going to know which drive to believe, and so about 50% of the time, it's going to get it wrong. But let's actually test it and find out. Okay, so let's just do an fdisk-l, yes, dev SDA 1.4 terabytes, good. Let's do mount dev SDA1 to sandbox. Mounted, no errors. Looks like all of our stuff is there. Our results file, it appears to be intact. Dummy 0 failed. Dummy 1 is okay. I'll go ahead and spoil it for you now. About 50% of our files are going to be screwed up. And the reason for that is because, remember, in the RAID video, I talked about how the actual parity information is striped across all of the disks in an array. There's not just one disk that's reserved for parity. Because we have hopefully reasonably randomly written sectors all across our disk, about 50% of our files, 50% of the 1,000, about 500 files, because the disk is full, remember, will have some corruption in them. And that's because about 50% of the time we will have hit a data block, and about 50% of the time we will have hit a parity block. And so when the controller encounters this situation where there's an inconsistency between the data and the parity, it's going to go with the data and ignore the parity. And so where we've introduced corruption in the parity, nothing bad happens. But where we've introduced corruption in the data, it's going to go with the data and ignore the parity, or correct the parity. It's going to rewrite it. And so this is actually the worst possible situation. Because this drive is kind of working, the controller, if it's going to correct the situation, is going to look at it and say, okay, I've got data block 1, data block 2, and my parity block, because it's 3 drives. And one of those 3 is wrong, but it doesn't know which one, and so it's just going to go with the 2 data blocks and ignore the parity block. But because of what we've done, and because the parity is striped across all the disks, any of the data disks that we have, any of the data blocks that we've corrupted, it's going to keep those and trash the parity that it could use to correct the file. But the reason it can't correct the file is because it doesn't know what the correct file is. We know because we saved the MD5 sums, like we saved the hashes of the file, and so we know which ones pass and which ones fail. If it weren't for that, we wouldn't know which ones pass and fail. We would just know there's corruption there. And that is the difference between a modern file system and an older file system. And that is why hardware RAID controllers, at least hardware RAID controllers that don't add extra error detection information to the disk, which would make that RAID 1 situation we talked about not work. When we have controllers that don't do that, then it's a problem. And so I think that there's going to be a new generation of hardware RAID controllers that actually don't, even in RAID 1, don't really write to the disk as sort of a pass-through mirroring situation, that they write extra parity information to the disk. Honestly, they should already be doing that. They don't, but they should. SANs do this. Not all SANs, but a lot of SANs have the same type of functionality that you see on ZFS and BTRFS and other file systems, where it is storing, in addition to the file, some checksum or parity information to detect when one of the drives is lying. If the controller had some way of knowing which drive had bad data, in this situation it could correct it. Because remember, we've got 2 out of 3 drives. RAID 5 says that should be a perfectly fine situation. It should totally be able to recover from that situation. But because the controller doesn't know which drive is lying, it's not going to be able to recover. And so this is the situation we find ourselves in. And so the hardware RAID controller really no different than the software RAID controller in that respect. Now, is the hardware RAID controller better in terms of write hole, in terms of caching, in terms of performance, in terms of all sorts of other things that can get you into trouble on your RAID array? Absolutely. Go with hardware. Do not use software RAID if you can possibly avoid it. Hardware RAID is really the way to go. But even using hardware RAID, you've got to understand what's happening underneath the hood. And if you don't, you're going to run into problems. And you're going to ask yourself, it's like, why is my data corrupt? I don't understand. It was RAID 5. Well, now you know. All right, basically what we're going to do to get started is we've looked at a couple of different options, a couple of different controllers so far, and they have all failed us, basically. Linux MD has failed. LSI hardware RAID controller has failed. Let's give BTRFS a try. Now with BTRFS, you've got to do direct a direct connection to the disks, so it's not going to go through a RAID controller. It's just going to plug directly into the motherboard. And so what we need to do is set up BTRFS with RAID. Now BTRFS really only does RAID 1 at the moment. It doesn't do RAID 5 or 6. Disk replacement is sort of challenging. There are some patches, kernel 4.0, there's some stuff running around. It's not ready for production, it's not ready for the prime time. The wiki also hasn't been updated in a while. It's really the distros that are driving development on BTRFS, and not really, it doesn't seem like it's as much on the kernel side. See, usually the kernel is the bleeding edge, and then the distros adopt what's happening in the kernel. But it seems to be that with BTRFS, the distros are the things that are actually driving it, and then it's sort of making its way back to kernel.org in the BTRFS documentation. So with our particular distribution here, we did not have it, so we're going to apt-get install the BTRFS tools in order to set it up, which is going to grab a kernel module for our running kernel. It's going to recompile the initial RAM disk in RD and set it up so that when we reboot, BTRFS will be available. So we've got our two disks, SDA and STB. Those are our 698/750 gigabyte, depending on how you count, disks that are ready to go for BTRFS. We're going to mkfs.btrfs and specify that we want both the metadata and the journaling stuff. That's one set of redundancy, and then the data redundancy for the other part. We're going to use mkfs.btrfs-d RAID 1 because that's going to set up the data in a mirroring configuration, and also -m for the metadata so that it is also mirroring. And we're going to specify dev SDA and dev SDB. Now, if you notice, when it does this, it's sort of weird because it says, okay, sector size 4096, size 1.36 TIB. Okay, so it's 1.36 terabytes. It's basically double the disk. This is confusing to me. It's not really. It's annoying. But I know why they did that, but it makes me crazy anyway. So yes, this is a RAID 1. It's not a RAID 0. So with BTRFS, when you specify RAID 1 and when you specify data, there is a plan for BTRFS that later, at some point in the future, you will be able to, on a file-by-file basis, specify the level of redundancy that you want. So if you need to create a file that's not actually mirrored on two different devices, then you can create a file that's not actually mirrored on two different devices, and so it wouldn't actually take up the space. Now this thing is saying it's 1.36 terabytes, like as if it was a RAID 0, or like as if it was JBOD, just putting the disks together. And the reason for that is because eventually BTRFS will let you specify different levels of redundancy, and so you could actually create a file that is not actually mirrored across both disks, and so they have to report it as 1.36 terabytes. But when you have a 500 meg file and you write that 500 meg file to the disk, it is going to take up twice as much space. Except in this case here, because by default the BTRFS also uses compression, and so because we are going to create a 500 meg zero file filled with zeros, it's not actually going to create a 500 meg file filled with zeros. It's going to compress that, and so we will have to remount it without actually having any compression. Like, we will have to turn off compression when we mount it in order to get our zero filled random files to actually take up the amount of space that they say. The other thing with BTRFS, which we will see much later in the video, is that when I'm doing the DF to find out how much free space that there is, it's not reporting anything that seems like is correct. And that's because it's not recalculating. It's not actually recalculating the amount of free space every time. It will do that when you mount and unmount the disk and periodically, but it won't actually do it, every time. The other thing that was interesting is that as we're generating our 0 byte filled files, it's insanely fast at first, which tells me that BTRFS is using an ungodly amount of system RAM as a cache, as a write cache for the drives, because the first few 500 meg files that we create are written at something absurd like 2.2 gigabytes per second, even with the compression turned off. And this is basically owing to BTRFS taking advantage of the free memory on the system and having a ludicrously huge file cache. I'm not really sure what the specific parameters of it are, because BTRFS is kind of a new thing. This same type of thing exists on ZFS and other modern file systems. In ZFS's case, I think it's 2 seconds. Like, ever how much data can be written in 2 seconds is how much it keeps in memory, which might be an absurdly large amount of data if you have a whole bunch of spindles or you have a really fast array. When we're going through this, the write here, it's really fast at first and then it tapers off, so that's probably okay. The other thing that we wanted to try was writing from dev urandom to the files, just to show you how that would behave. Now, reading from dev urandom is actually pretty slow. It's only about 13 or 14 megabytes per second because the system is trying to generate random information, and it actually takes a lot of computational horsepower to generate a lot of random information. And so 13 to 20 megabytes per second off of dev urandom is pretty normal. And so by doing that, we even still got a lot of compression. And so because there's compression, that should tell you that it's not especially random, but it is somewhat random. And so even reading from dev urandom, and we check and see how much space is used, it's a little less than what we expect. And so part of that is because of the fact that the free space is only calculated periodically because of the way that the file system is mounted. And part of that is also because compression is still enabled. So we need to disable the gzip compression. And so we're going to unmount it and basically remount it with some different parameters. Okay, so we're going to do mount-o compression equal no, or compress equal no. And we're going to try the same thing again where we just write a 0 filled file just to show you what it's going to do. 1048576 is 1 megabyte in binary. All right, so now it's showing 873 megs is actually used, and our use space is about 1 terabyte. So this is about what one would expect with the compression disabled. So that's one of the interesting things about BTRFS. So even though I've got 700 gig disks, 750 gig actually, is reporting 1.3 terabytes of free space. If I were to try to write 1.3 terabytes to the files to this, it will fill up halfway through, because every time I write a file, it's actually writing the file 2 different places. And so this is sort of strange, but the reason they did that is because at some point you will be able to write files to the file system and actually say this file is redundant, this file is not redundant, this other file is redundant, this other file is not redundant. And so you could actually write 1.3 terabytes of information to the file system if you specified that all of the files that you were writing were to get no redundancy information. However, I don't believe that those features are working properly right now. I think that eventually they'll probably change it so that, like, the way that we've configured this file system is that by default the files are written with redundancy information. I think that they'll probably change the algorithm so that by default it's reporting the amount of free space that you would get, like as if it's taking the default behavior into account. So that's how everything else under the sun does it. They will probably do that eventually. But again, new file system, new technology. Somebody somewhere was like, it should be like this on purpose, and I really don't see a good reason for it, other than what I've explained, which doesn't seem like a good enough reason. Because hey, we've had file systems with compression for years, and those haven't really reported the expected compression. It's like, oh, your files on disk have a 1.1 to 1 compression ratio. Let's report 2 to 1 free space, because we expect 2 to 1 compression. Not since DOS has it been like that. So, and that was a bad version of DOS. So we will mock it. Okay, so this is our standard MO. We're going to create a gazillion files that are all zeros and get the MD5 sums of every single one of them, store that in our results file. So we've done that. This volume is now completely full of files that have redundancy information, and we've got the list of MD5 sums. And so we're going to just do some quick spot checking, make sure that we've got our results file, copy it out of our sandbox, and we've got a whole bunch of files here. So this looks really good. Then we're going to unmount it so that it's no longer mounted, and then we're going to introduce corruption onto one of the drives in the volumes, and then we're going to run our MD5 sum checker and see if we see the same level of corruption. Now, same deal as last time, we're going to write 4,000 2 kilobyte sectors all over the place, just randomly. In fact, it's the same set of sectors as last time. So we're going to just fill those with data from dev urandom, but only 2 kilobytes per write and 1,000 writes. So we've got 1,000 lines in our random sectors file, and we're just going to run this and let it complete. And then we will have introduced 1,000 2 kilobyte spots of corruption all over the disk in just random places. Okay, so this is going to town, writing our 2 kilobytes of terribleness all over SDA. So SDA is now corrupt. So the next thing we're going to do is mount remount our sandbox, which is BTRFS, and then we're going to confirm that the mirror is still working by creating a folder on the corrupt drive, and then unmounting it, and then mounting the other drive, and just confirming that the folder that we created is still there. It kind of wigs me out just a little bit that I can specify any device, and when I specify any device to be mounted for BTRFS, it finds all of the devices. It's like, not used to that. Makes me paranoid. All right, so we're going to create test, testy, test. We're going to unmount it, and then instead of SDA, we're going to mount SDB and make sure that testy, test is there. Yes, it is. And just because I'm OCD, we're going to unmount it again and mount SDA one more time. Now let's run our MD5 sum checker. Again, RAID 1, 50% of the files probably have issues. Now the next thing I wanted to do was actually see if I could find in the system where it's reporting a checksum mismatch, or it's reporting an error, or it's reporting that it found something wrong and that it's going to correct it. Because the expected behavior of BTRFS is that it will do the correction. Because again, this file system is doing stuff behind the scenes, and so it knows that something has gone wrong with one of the drives, and it knows that it has another copy of the data on the other drive. And so when it encounters a problem reading from the first drive, it'll just read from the second drive and get the correct information, and then report that back to the MD5 program. And so as you can see, we're already 11 files in and 12 files in, and there are no errors. And statistically, the chance of this happening without BTRFS doing the error correction in the background is about 150,000 to 1. So BTRFS is clearly doing its job, but checking the kernel messages and checking other places in the logs, it wasn't actually reporting any problems, which is sort of weird. It's not actually logging them anywhere. I guess on the BTRFS wiki, there was something about you can hook something in the kernel and it'll output a debug message from the kernel, or if you get a kernel panic, you can debug the kernel panic and then it'll report that. But look, we're 20 files in, there's still no errors. Clearly BTRFS is doing its job, but it's also not telling us that it's doing its job. And so it turns out the answer is there's a BTRFS Scrub command that's fairly recent. There was some documentation that I read on the mailing list with BTRFS, and it was like, oh, you just need to rsync or copy the files and then it'll do the scrub thing. But there's actually a scrub command now, which is like ZFS and like other file systems. And so what the scrub command does is actually go through the file system and report errors. And so that's what we want to do next. And so what we're looking at is the man page for BTRFS-Scrub. Now, if you haven't used man is it's like a built-in manual for everything on your system, although usually it's just easier to go to the wiki and look at stuff in the wiki because sometimes the man pages are not as up-to-date as they should be. And so in this case, BTRFS-Scrub, which will scrub the file system. Now, I thought about it. It's like, oh, let's unmount the file system and scrub it. But you actually probably want to scrub your BTRFS system weekly or monthly. Maybe more often than that, maybe less often than that. But what that does is that goes through the system and it looks for any corruption, and it will correct any corruption that it encounters. And unlike the situation with MD and the LSI RAID controller, it actually knows which one is corrupt and which one isn't because of the hashing and the MD5 sum calculations and that kind of thing. It's not just that it's reporting bad data and it's like, oh, I don't know which one of these to use. There's actually mathematical clues as to which one is the correct one to use. And so to do that, we just need to do BTRFS Scrub start -B -D because we want to actually output this. And they're actually also going to specify -R, which is not actually going to correct any of the errors. Now, to run this command will take a long time to run across the full volume, but remember that statistically, those points of corruption that we introduce to the drive are randomly scattered throughout the drive. So odds are it's going to encounter one pretty quickly. And so we're just going to Control-C this real quick so we can take a look at it. It's like, all right, it got through and it found 13 errors. It didn't correct any of the errors because we told it not to correct the errors. But after 7 seconds, it encountered 13 errors. So let's let it run a little bit longer. It's also interesting that I specified to run it against dev SDA, and that ran just fine. But the second time around, I'm going to have it actually run against Sandbox, which is our mount point. And so that worked perfectly fine as well. It encountered 44 errors, but again, because of the -R command, it didn't actually correct them. So let's run this again without the -R and see if it actually will correct the errors now. So those of you at home that are running BTRFS, have you set up a cron job with BTRFS Scrub start? And are you emailing yourself the results of that cron job? Because you probably should be if you're not. All right. So this is corrected 34 errors. So what we would do is let this run across the whole drive. And when we let this run across the whole drive, the corruption that we introduced on the first drive will be corrected using information from the second drive. This is great. This is exactly what a modern redundant mechanism should be. Whether this is implemented in hardware or software, there's not really any hardware out there right now that does this that I'm aware of, other than SAN hardware, of course, which is really just this kind of software running underneath, because the SAN is almost always a server grade computer with a whole bunch of disks attached to it. ZFS works basically the same way. If you're interested in ZFS instead of BTRFS, be sure to check out our FreeNAS build video. We've got an updated version of that coming out soon. But this has been sort of a quick overview of BTRFS. This has also been the second part of our RAID series. So if you missed the first part, be sure to take a look at the first part. The second part is really just exactly what did we do? And so, just to recap, we looked at MD. MD has, when you introduce corruption with MD, MD can't recover from it. Even if, all of the disks are present, you actually are better off if you pull one of the disks that has corruption. So MD fails. The LSI hardware RAID controller, when you get bit rot and one of the drives flips bits, it fails because it doesn't know which one to recover from. BTRFS RAID 1, the downside is you really can only do a mirror with BTRFS. It doesn't really handle more than 2 drives well at this point. I guess you can do a RAID 10 with this setup, but RAID 5 or RAID 6 really is not a good idea. So I think modern file systems like BTRFS and ZFS that have protection and error correction information that work in conjunction with the hardware that's running underneath are really the file systems of the future, especially when we're talking about multiple terabytes and terabytes upon terabytes, hundreds of terabytes. When we're talking about file systems like that, then this is a more appropriate solution because it provides a level of redundancy and a level of error correction that most hardware setups don't provide. That's been part 2 of the RAID series. If you guys have any questions or if there's anything that we missed, hit us up in the forums over at techsyndicate.com. Until next time.